In this video, we'll cover hydrolysis of salts. What are exactly salts? Salts are ionic compounds made up of a cation and an anion. Cation are something with a positive charge, and anion would be something with a negative charge. So ionic compounds are made up of a cation and an anion. Now, when these salts are submerged in water, what will happen is that these compounds will start to break apart. And when they break apart, in the beginning, they might stay like this intact. And when they get submerged in water, they will break apart with positive and negative like this. Now, at this point, it may produce an acidic or basic or a neutral solution depending on what this compound is. So let's take an example of the following, and we're going to look at the acid, something that will produce an acid solution. So here is ammonium chloride, and in the ammonium chloride, when it's submerged in water, notice it's solid, and in submerged in water, they break apart into its cation and an anion. The cation, you can see it. You might notice that this is an acid, and you might notice a chlorine here too. But what is it going to produce? Is it going to give you an acidic solution, or is this going to be a or basic, or maybe perhaps a neutral solution? So let's look at these NH4. Well, we know that when NH4 interacts with water, since it's an aqueous form, it's in here, right? The positive is in water. It's going to interact with water, where in which the hydrogen will donate its where it's going to donate to the water to form a hydronium ion, an NH3, and it has a value associated with it, and this can be found in the chart, or you could find it in the Kb and sulfur Ka, but here I'm going to already give it to you, and so it's going to have a Ka value. What about chlorine? Will that interact with water? Well, when chlorine, so here, this is an acidic ion, so you could tell by the Ka value. Sorry, I forgot to note that. And what about the Cl? Well, the Cl, when it interacts with water, it can potentially take out the hydrogen and act as sort of a base. However, notice that the Kb value for that to happen is considerably really low in comparison to the Ka. The conjugate, another note here is the conjugate acid of this base over here is a really strong acid. So what that means is the likelihood is going in that direction where the base plucks off the hydrogen. It's probably not going to happen. And if you were to say this has no reaction, I pretty much agree with you, but there is a Kb value, and that's really low, okay? Now, if you compare the Ka and the Kb, notice that the Ka, though it's low in comparison to the Kb, it's significant. So therefore, this would be considered to have an acidic solution. Okay, an acidic solution, because sort of like that Ka overpowers the Kb. And so you're comparing the Kas and the Kbs here. Knowing that, let's do a learning check. A salt, ammonium chloride, so here, okay, is submerged in water. So this is a solid that is submerged in water, and you notice that it has been split apart. What is the pH of the solution in a 0.233 molarity of aniline chloride? Okay, so let's talk about this one right here. The ion here, the very first ion, what will it interact with? Well, it's going to interact with water to form what? So I'm going to rewrite this, C6H5NH3+. It's going to interact with water. So it looks like it's going to be and it's giving you a Ka value. So what does that mean? This is probably going to act as an acid, so therefore it will donate and C6H5NH2, and then it's going to get rid of the H, and instead of the H2O, it becomes H3O plus. So this is aqueous, and so is this one. Liquid, and this is aqueous. Now we can show that in the very beginning, this had 0.233 molarity. Now you might say, well, it's 0.233 of aniline chloride, not this ion here. You're right. But because this is a 1:1:1 ratio and showing that this is going to all kind of dissociate, okay? It's going to all dissociate into this 2 counterpart. The concentration of this will equal the concentration of this and also even the concentration of this. This is chlorine, not the plus sign. All right. So therefore, we know the concentration of the ion counterpart is the same as what the salt was. Okay. And then so therefore, it was, here's ICE table. Here's an ICE table in which we have the initial, there's none of these guys. And there's a change where it starts to diminish, so minus X, and this will start to increase in product, so plus X. So add the top and the bottom together, and then you get these. So something that's been repeating over throughout this particular unit. So if I were to set up the Ka equation for this, is concentration of C6H5NH2 with hydronium ion all over the initial. Okay, and then we can also show that this is X times the X based on over right here, okay, and all over this guy. So that's divided by 0.233 minus X. So if I were to rewrite this, including the Ka value, it's 2.3 times 10 to the negative 5 is equal to the X squared, and then 0.233 minus X. Now, because the Ka value is quite low, it's lower than 0.001, we're going to ignore this X value, and X squared is then equal to 2.3 times 10 to the negative 5 with 0.233 on the bottom. Okay, we're going to multiply 0.233 both sides. And then I'm going to cancel this out, and then you're left with X squared is equal to, if you were to multiply all of these together, it would be 5.36 times 10 to the negative 6. So if you are watching this video, just pause and see if you're able to calculate this out. And then you square root this. And X, therefore, is equal to then 0.00231. Now, what does that mean? Well, this X represents the concentration of the hydronium ion. So H3O plus is equal to this particular number, 31 molarity. So why is that so important? Because we want to know pH, and pH is the log of the hydronium ion. And now that we have the concentration of the hydronium ion, which is 0.00231, we can calculate the pH. So you plug it in, and you should get 2.6. So what does that mean overall for after knowing this pH? So we know that this is an acidic solution. Remember, acidic solution is anything below the 7 on the pH mark. Here, what it says, the next learning text is, what is the hydronium ion concentration in a 0.100 molarity solution of ammonium nitrate salt? So this is the salt composed of the ions of ammonium and nitrate. okay? Which is a stronger acid? After that, you're going to find out which is the stronger acid. So is it this one or this one? And this is in comparison to the previous learning check. So you'll have to sort of do a comparison. See if you're able to find the concentration of hydronium ion first here. And then we'll go on from there together. All right, so coming back, I found the concentration of hydronium ion. Something to kind of give you a little hint on how I went about this. You'll notice that I gave you a Kb value, but not the Ka. The ammonia, it acts as an acid, however, so you needed to find Ka. In order to find Ka, well, right here, you do the Kw divided by the Kb, which is 1.8 times 10 to the negative 5. So after finding the Ka value, I was able to set all of this up and find the concentration of the hydronium ion. So this is my concentration of the hydronium ion right here. Okay. Well, that's taking up a lot of space here. Now, if I were to take that in comparison to the hydronium on the previous slide, right here, which is 0.00231, okay? So the previous slide had 0.00231. This is from the previous slide. That's the molarity. Which is a stronger acid, meaning which one is more concentrated? Yeah, this is more concentrated, which means that the C6H5NH3 plus, this is your stronger acid, okay? This would be your stronger acid. If you can actually plug this into your pH and then find out the pH, and you'll probably notice it's higher than 2.6, and that's kind of like how you know that this is a acidic, less acidic than the other one. Okay, let's move on. And that would be for base. And we already know that salts are ionic compound made up of cation and anions. And when they're submerged in water, we know that they're going to split off. And when they split off, it's going to either form acid, base, or neutral. And I want to focus now on a basic solution. So here you'll notice that there's a NaCH3 CO2 forming into sodium. That's your cation splitting off into an anion splitting off. Now, what happens when these guys are by itself interacting with water? So first of all, let's talk about this this portion here. When that one is in water and it gives you already the Kb value, and the Kb kind of value already like rings the bell, showing that it's going to have a basic solution. And so therefore it's going to interact with water. Hydrogen will be donated to this base, and then it's going to form into this neutral compound. Now, what about for sodium? When sodium interacts with water, will it pluck out hydrogen? Well, think about it. Hydrogen is what charge? It's positive. It's a proton, right? So what is the likelihood of the sodium, that Na plus, is really desiring the hydrogen? Not likely. There's not going to be any reaction with the water. It's not going to pluck out anything. So you leave this as a basic ion, but the sodium with water, there's not going to be a reaction where we might think that this will act as an acid, but it doesn't, even though it has a positive charge, because it's not going to form HNA, okay? I don't know what HNA is, but it will not do that. There will be no reaction. And so therefore, and there's no even a Ka value to it. So this, therefore, it's only determined by Kb, this particular salt. And so this will be a basic solution. So a learning technique based on this would be as follows. Right, it says determine the acetic acid concentration in a solution with CH3CO2 minus equals 0.050 molarity and hydroxide at 2.5 times -6 at equilibrium. So kind of nice. It's already giving me the equilibrium concentration. The reaction is as follows. You can see the base plucking out an H, so it's formed an acetic acid, and then you have a hydroxide here. Now we can say Kb, since this is acting as a base, Kb is equal to the concentration of these guys, hydroxide, all over its counterpart here. And we want to know the concentration of the acetic acid. So we want to know concentration of this. This is our, what is this? Okay. We actually have almost everything. You might think, okay, well then what is the Kb here? So Kb for this, you look at the base ionization constant and you'll notice that it's not there. But we actually have the conjugate acid Ka, which is right here. What does that mean? Well, we know that Ka times the Kb is equal to Kw. We have Ka value, so Kw divided by Ka is going to give you your Kb. So Kw is 1.0 times 10 to the negative 14, and then this is 1.8 times 10 to the negative 5. If you solve this out and I plug it into a calculator, which I already done for you, but you should try it on your own, of course, and it's 5.6 times 10 to the negative 10. All right, so now that we know the Kb value, we can sort of plug everything in. Kb is 5.6 times 10 to the negative 10 is equal to the concentration of this one. And then you have your hydroxide, which is, let's see, I can just go ahead and put that in straight because we're running out of room. Let's get rid of these guys, okay? This would be 2.5 times 10 to the negative 6 all over, the bottom is 0.050. Okay, so you're going to solve for this, and come back and check this video. And here is the key.